Today we'll dive deep into understanding the CI. I am Rajul Tani, a machine learning engineer here at Ivy. So today we'll learn about continuous integration, which is basically responsible for all the tests that you see running on the Ivy repository. So let's start. Yeah, so we follow the practice of CI in order to regularly build and test code at Ivy. So this basically has two advantages. One, the developers get feedback on their code soon. So like errors in the code are detected quickly. And second, the developer can easily debug the code when finding the source of an error and roll back changes in case of like issues. So in order to like incorporate continuous integration in the Ivy repository, we follow a threefold technique which involves commit trigger testing, periodic testing, and manual testing. We use GitHub Actions in order to implement and automate the process of testing. Yeah, and GitHub Actions basically like allow us to implement custom workflows that can build the code in the repository as well as run the tests. So for anybody who's interested, all the workflows used by Ivy are defined in the .github/workflows directory on the Ivy repository. So yeah, the most significant part of the CI is commit trigger testing. So basically it involves running tests on each commit to make sure that the commit does not introduce any new test failures. So we have like two types of tests to run, the IV tests and the array API tests. So the array API tests are like borrowed from the array API consortium and like make sure that the IV functional API adheres to the standard. The discussion like we'll have here would mostly be centered around the IV test. An IV test is basically defined as the triplet of submodule function backend. So basically the notation given here is used to like identify each test. So we first have the submodule followed by like so yeah, like here's the submodule followed by the function being tested and followed by the backend. So for example, like here we are testing the torch instance arctan function of the tensor submodule with the NumPy backend. So yeah, that's the thing. Yeah, we'll also be incorporating versioning into this. So for each of the tests that runs, there would be like a backend version, and for each of the front end tests that run, there would also be like a front end version. So the notation would basically extend to take in those into account as well. So yeah. So yeah, the natural question we have here is, so can't we just like trigger all the IV tests on each commit made to the repository? A simple like back of the envelope calculation suggests strictly against this. So number of tests running on the repository without taking any framework or Python versioning into account is like 7,284 as of making this presentation. And like we are adding tests daily. Therefore, like triggering all the tests on each commit is neither desirable, like as it would consume like a significant amount of resources, as well as take a large amount of time to run. Not feasible, like as each job in GitHub Actions has a time limit of 360 minutes and a memory limit as well. So further, when we consider like versioning for a single Python version and like about 40 front end and back end versions, the tests would shoot up to 40 cross 40 cross 7,284, which is actually 11,654,400. And we obviously like don't have the resources as well as the time to run those many tests on each commit made to the repository. So we clearly like need to prune down the tests that run on each push to the GitHub repository. Yeah, so the ideal situation here is to trigger like only the tests that are impacted by the changes made in a commit. The tests that are not impacted by the changes made are clearly like wasteful to trigger as their results don't change. For example, like consider the commit mentioned here. So as shown in like the screenshot here, the commit changes the reduce loss and the binary cross entropy functions in the IV functional like losses.py file. So the reduce loss function and the the binary cross entropy function is like sort of changed like as you see here. So in the IV functional like losses.py file as mentioned here. So the only test that like must be triggered like for all the four backends, NumPy, TensorFlow, PyTorch, and JAX in the ideal situation like are listed here. So IV's functional API functions binary cross entropy with logit, stressed cross entropy, test binary cross entropy, test parse cross entropy are like the first four of these are like clearly impacted by the changes in the commit and like thus these four tests should be triggered. These are basically testing the IV functional API functions itself. So yeah, which sort of directly call the like changes if they commit. So clearly like these can have their results change and therefore they should be triggered to check if like the changes in the commit have made some of them to fail. And then since the torch front-end functions, torch binary cross entropy, this one, and the torch cross entropy are like wrapping these functions of the IV functional API. Therefore, these two tests should also be triggered to make sure that like these like are not like getting failed because of the changes made in the commits. So yeah, like no other front-end functions like wrap these like underneath, and hence like they should not be triggered. So the question here is like, how do we achieve this, or at least try to reach this ideal scenario? So yeah, let's move forward. In order to like implement this, test coverage plays a crucial part. So test coverage refers to finding statements or lines in your code that are executed or could have been executed on running a particular test. For example, if I consider the test binary cross entropy with the NumPy like backend, it will like cover the binary cross entropy function defined in the IV's functional API as well as the NumPy API functions it would have been implemented using. So yeah, like in order to like find the test, like find the coverage of a test, we use the Python coverage package. Yeah, and like for determining the test coverage of any of the tests, the way it works is by running the corresponding PyTest and then logging like each file, each line of a code that was executed or could have been executed for each test. So basically, you sort of trigger the test and then sort of keep logging that hey, this file and this line was executed. So yeah, like computing test coverage for all the tests like allows us to find for each line of code which tests affect the same. So basically, if a particular line is triggered, like is sort of covered or like executed when like we have triggered a test, this means that changing that line in the code would definitely change the status of the test. Not definitely, maybe, but like has a chance of changing the pass or fail status of the test. And therefore, if there is a change in that line, we should definitely rerun that test to make sure that like the change has not made any significant change in the test result that like earlier it was passing and now it has started to fail. So so yeah, basically like computing test coverage allows us to find like all the lines that like affect a test. So basically we can create a mapping dictionary to store this information like as shown here. So the actual mapping we compute is a bit different from this design, but like we'll follow this for now due to like pedagogical purposes. The dictionary stores a list for each file f1 to fm as shown here. Has a like there's a like list for each of the file, and then list is this list is basically a sequence encapsulating the lines of the file. So like each index of the list contains like a set of tests. So basically like this one is for like line number, like the first line of the file f1. This is for the second line of the file f1, and so on. This is for the last line. um and yeah, so basically each index here, like each entry of this list uh like contain the tests that are corresponding to the like to the test mapped here. So for example, like t1 is like impacting the second line of file f1. Like it's so basically if like there is a change in f1 second line, we should definitely trigger t1, t3, and t7 because like while executing t1 it coveraged the second line of f1. So yeah, moving ahead, uh, given this mapping for a commit, we can like just follow the procedure like given here. So to get like to sort of find the like in order to find like which test should be triggered on a like particular commit. So first step is to like finding the files which are changed in the commit. So and checking for like lines that are added, deleted, or updated in the file. Next, like we need to determine the tests that impact the lines, and finally just trigger like these tests and like no others. So so yeah, like sounds like a reasonable approach, and like the implementation is facilitated partially by the PyDriller Python package. And like, yeah, I've used some of the low level functions from the package to implement a custom method to find the changed sort of files between any two git commits given their hashes and the exact sort of changes in the files. So yeah, there is some sort of partial source code given here. So yeah, I'll try explaining it in some detail. So we basically first take a diff of the two commits, like the commit like previously we have the mapping for, and like the new sort of commit, and then we basically like so we have like named this the ref commit for the reference commit, and the commit for the current commit. So and then we basically parse the diff to get an iterator of the modified files. Each file contains a diff parse dictionary from which like the added, deleted, and updated lines are computed. So for any two sort of commits, a reference commit and like the latest commit, I can find in like each of the line in each of the file that is added, deleted, or updated. So yeah, moving ahead, like this approach sounds like workable, but there's a fundamental issue here. In order to determine the ideal test to run on a commit, we need to compute the mapping, and then like computing the mapping requires determining the coverage for all the tests, which in turn involves running all the tests. So that's what like we wanted to avoid, right? So this clearly sounds cyclical, and after all, like we are doing all this to avoid running all the tests on each commit. So yeah, how do we handle this issue? Mm, so for some moment, assume that we had some way to compute the mapping for a commit from the previous mapping without having to run all the tests. So like then given the mapping for some initial commit, we could follow this to determine and run the relevant tests for each commit, like as shown in the diagram here. And we keep using this update mapping black box, this one, to compute the current mapping and then use that mapping to determine and run the relevant tests. So since we do not need to like compute the mapping on each commit, we need not compute the coverage for all tests, and thus we need not like trigger all the tests on each commit. So like that breaks the cycle. So if we are somehow like magically able to generate the mapping for a particular commit as it comes, we can like do this and determine and like run the tests, run the ideal tests that are sort of relevant to be run, and like may have their status changed. So yeah. So yeah, let's unwrap this black box of update mapping. How do we sort of generate the mapping for a particular commit from like the mapping for an older commit? So this is like exactly what we do in order to implement what we call intelligent testing. So the update mapping logic works like as given here. So we follow these steps for each file change in the commit. So we can get like the changed files as I showed, as I had shown earlier, using the PyDriller Python package and like doing some low level sort of implementation using that. So first of all, for each deleted line in that file, we remove the corresponding entry from the list map to the file in the mapping. So this is like a pseudocode that does that. Like so I get the test for that file name and store it in test underscore file, and then like for like every line that's sort of deleted, I can just like delete the corresponding entry from the test file sort of variable. So yeah, it's done like in reverse order so that like we don't change the order, like we don't have like the list deletion issues. So yeah, but yeah, that's just an implementational detail. um Yeah. So yeah, like, and then for each line added in the file, we compute the test as an intersection of the set of tests on the line above and below the line. So I've like given some verbatim code from the determine test script, which basically involves the test file variable. This is the list corresponding to like the changed file. So yeah, like test file sort of contains the list corresponding to the changed file. Um, yeah, so yeah, that's basically it. And then finally, for newly added tests, like we compute the coverage of the new tests. So there would be like some tests that are added like just in the commit that we are seeing. So basically we would need to like compute the coverage of these new tests and update like the mapping correspondingly. So this is like limited to 10 new tests per commit, so that if you end up like adding like multiple tests in a given commit, we don't like trigger all of them at once, as we don't have like the bandwidth, both in terms of memory as well as the time to run coverage for any more than 10 tests in a single run. So if more than 10 new tests are added in a commit, the new tests are queued in batches of 10 for like further commit. So like 10 would be run in the first commit, and then 10 in the second, and so on. So yeah. And then clearly, like, all of this that we are doing is going to distort the mapping as we go like deep into the commit sequence. So like whenever we call the update mapping once, the mapping would deviate slightly, like it would have minor deviations from the ideal mapping for that commit. Then again we would like call the update mapping subroutine, and it would have some more sort of deviation from the like ideal mapping. And in the worst case, as we sort of go like ahead in our commit sort of lineage, we would eventually like have a mapping that is way too deviated from the ideal mapping. So we don't want this to happen, and therefore, like once the mapping has been updated, and therefore we use sort of the determine test coverage workflow, which I'll talk about in like in like these after I think a couple of slides. So yeah. So once the mapping has been updated, the determine and run test logic works as like shown here. So for each line updated, added or deleted, we collect the test corresponding to the line. So like if you have changed line number 2, 3, and 5, you have maybe added some lines or deleted some lines. And then like I'll collect like all of the tests corresponding to that, and then sort of like trigger all the collected tests along with like the newly added tests in the commit. So yeah, so the triggering of tests happens using the run test.py script, uh, which is sort of responsible for one triggering the test, and second sort of updating the latest status of that test in a MongoDB database, which is sort of used like for us like for a dashboard that displays the latest test results like conveniently to the users. And I'll talk about that in the last part of this video. So yeah, like that was a bird's eye view of the system. And now let's like deep dive into some details of how these parts are actually implemented. The first thing that we talk about is storing and retrieving the mapping. So the mapping has to be like stored somewhere, right, in order to be used by a future commit to determine the corresponding mapping and like therefore trigger the required test. So since the update mapping subroutine requires the mapping for a older commit in the history in order to generate the mapping for the current commit, I would need to sort of store and retrieve this mapping. Therefore, we need a mechanism to store and retrieve like this mapping on sort of each commit made to the repository. So we use like the unify AI slash mapping GitHub repository for this purpose. So we use a GitHub repository like for the like given reason. So the best part about using a GitHub repository is that it has built-in synchronizations and locking mechanisms. So basically the ability to point out merge conflicts and to handle a shared object is integral to GitHub, right? So this helps us avoid a severe race condition issue, which I'll like go into the details of in some time. And so yeah, that's one reason. Second, the repo is like public and thus can be read by anyone while the push can be restricted. So like this makes it helpful to expose the mapping to run tests on the PRs as well, like while allowing only push commits to update the mapping. So therefore, like it sort of becomes naturally available to both PR based test and the push based test. So yeah. Thirdly, like unlike specialized database like Google Cloud and so on, we need not store any specific secrets to access the DB, and no separate API keys are required for updating the DB, saving us from like exposing our like secret key files via GitHub Actions. So in fact, we just need to store a single secret, which is the SSH deploy key. So yeah, that's also an advantage of using a GitHub repository. And finally, we need not make any specialized API calls to read, write, update the mapping. Like cloning and pushing to the repo suffices. So yeah. Just to mention, like clearly, a GitHub repository is not the best DB out there. Obviously, like with its own set of constraints. For example, like it does not allow you to put in like files with more than 100 MB sort of space requirement. But like yeah, works well for like our requirements. So yeah. Yeah, let's move to the next implementational details, which is like cloning and pushing to the repository. So for push trigger testing, the intelligent test workflow, like we use the SSH cloning method in order to facilitate the clone and push commands to the repository. Here is a code excerpt like which accomplishes the same. The clone mapping script first creates a directory called .ssh in the home folder of the VM hosted by GitHub. So like that's basically then supposed to copy the deploy key from the GitHub Actions secrets into the deploy key file within that folder. And then further, it adds like github.com to the list of SSH known hosts. So yeah, and then like now that the SSH key of the runner has permissions to push and clone the mapping repository, it simply calls the git clone command. And yeah, just to sort of like save bandwidth, we just do it with like the fetch depth of 1, so that we just get the latest commit and no others. So yeah, in case of pull requests, it works differently. We do not have like access to the SSH deploy key secret, and we don't even like want to give PRs that access, and thus we don't use the SSH clone methodology, and instead use the HTTP clone method. So and PR should not update the mapping on the repository clearly, and thus like no push is required in case of PRs. Um, Yeah, let's move to the next one. So the GitHub repository, as I mentioned, allows only storing files with like lesser than 100 MB of storage requirement. So the current design of the mapping that I like showed some minutes ago takes a significant space as test names are long strings and are stored repeatedly like for each line that is impacted by the test. So in order to reduce the space requirement for storing the mapping, we restructure this like mapping as follows. Like we include the index mapping and the test mapping fields, which map indices to tests and tests to indices. So respectively. And then so this allows us to just store the test index for like each line in the mapping, reducing the storage space significantly. So for example, like here F1, the file F1 earlier had T1, T3, and T7 support like stored in the like lines 2, but it no longer needs to store those long sort of test names, and instead just can store 1, 3, and 7, which can then be sort of like mapped to T1, T3, and T7 using this index mapping structure of the structure of this whole mapping object. So yeah. Coming to the next one, since each of our update mapping routine is like not precisely correct, as I mentioned earlier, the mappings like would keep aggregating incorrections as commits keep coming to the GitHub repository. So let's see how we should deal with that. Like in order to prevent this snowball effect from like running completely irrelevant tests on each commit, we need to recalibrate the mapping periodically. So this is done by the determine test coverage workflow, and it's implemented in the det test coverage YAML file, again in the dot github/workflows directly. directory. So yeah, just a fun fact here that the workflow triggers every Saturday night at 8:30 p.m. and like it's just my gut feeling that there are relatively less commits on the repository on a Sunday night and we get access to the resources quickly. So yeah, the workflow runs all the IV tests, determines their coverage and computes the mapping and like finally pushes it to the Unify AI/mapping repository. So yeah, like this is like a recalibration workflow. Um, yeah, so the determine test coverage workflow, which I talked about just now, takes about like 60 hours to complete if run with like a single runner. The GitHub action rules don't allow running a single job for more than 6 hours, right? So therefore, like determining the coverage sort of within sort of 6 hours becomes important. Like thus we need to split the workflow based on the tests so into like 32 runners. Each runner caters to its own subset of tests. So like we'll partition the tests and like assign each partition to a particular runner, and we have like 32 of these runners. So each runner basically caters to its own subset of tests and is responsible for determining the coverage for only those tests and creates the mapping based on these tests. So therefore, like we have 32 branches on the Unify AI/mapping repository, master 1 to master 32, and all 32 runners on the intelligent tests and intelligent tests PR workflows. And then like the mapping is pretty clear that the first one would sort of deal with the first one on determine test coverage workflow and the master one branch on the Unify AI/mapping repository. So yeah. Um, yeah, so everything sounds good so far, but like, can you think of a potential race condition issue here? Maybe pause the video and you can think about this. So yeah, the synchronized object here is the mapping repository and is accessed through like push, which is a write, and pull, which is a read to the repository. So the determined test coverage workflow and the intelligent test workflow can clearly run concurrently because like on a Saturday night, we can definitely have commits which would trigger the intelligent test workflow before the determined test workflow, determined test coverage workflow has completed. So yeah, and both of them write to the mapping repository. So therefore, like there is like a synchronized object, two threads, and then one of at least one of them is a write to the like shared object. So therefore, this is clearly like a race condition issue here. So in fact, I can like show a particular case for how it can like ruin up things. So consider like the following case for runner 2. The determine test coverage workflow has been running and is about to like complete for runner 2. Meanwhile, a commit made on the master triggers the intelligent test workflow. The runner 2 in the intelligent test workflow pulls the mapping from the master 2 branch of the mapping repository and starts running the determined tests based on like the changes made in the commit. So the dead test coverage workflow completes for runner 2, which makes like a push to the corresponding branch in the mapping repository. The runner 2 in the intelligent test workflow also completes and pushes the updated repository. Therefore, in the end, the push from the dead test coverage workflow would be completely ignored and the system would like never be recalibrated. Further, like for some other runners, the final push may be done by the determined test coverage workflow, and thus like the test distribution itself, like might get corrupted. Like we might have overlapping tests between runners, and then like some tests are clearly like missing and like are not allotted to any of the runners. So yeah, so we handle the race condition issue like as given here. So the intelligent test workflow is only allowed to push to the repository when there is no merge conflict, while the determined test coverage workflow makes a force push to the repository. So therefore, like when the above kind of situation occurs, the push from the intelligent test workflow is discarded while the recalibration push stays in place and leads to like consistency among the runners as well as like corrects the coverage. So yeah, we could only implement this solution thanks to GitHub's inbuilt synchronization metrics like merge conflicts and force push. So yeah, so that's also like a significant reason of why we resort to a GitHub repository to be used as a database for storing the mapping object. Yeah. So yeah, that was all about the commit triggered testing approach we follow. And Yeah, so we also run the array API tests other than the IV tests on each commit, just to mention. Yeah, and then in order to make sure that none of the IV tests are left ignored for a long time and to decouple like the rate of testing to the rate of committing to the repository, we implement periodic testing on the IV repository. The test IV cron workflow so is responsible, like it's also like linked here in the slide, so is responsible for like implementing this behavior by running IV tests every hour. In each run, like it triggers 150 IV tests, cycling through all of the tests and then updating their results in the MongoDB. So this number of 150 is chosen like in order to make sure that the action completes in like 1 hour most of the time, so that like we can then have the next cron job coming up. Um, so yeah, and then finally, we know that there can be instances where we will need to manually trigger tests, and thankfully GitHub Workflows allows us to take user input. So the exact code for this is available in the manual test.yaml file. And yeah, the workflow takes as input the name of the test, and you can specify like a particular backend, like this appended with a comma as shown here. So yeah, so if you want to run like this for just TensorFlow, you can just append like a comma here. And yeah, you can also like trigger manual testing similarly on a fork repository when reviewing a PR, and the exact steps are mentioned here. So yeah. Finally, in order to display the latest results of all tests at one place, we have like the dynamic dashboards in place. So yeah, like earlier we were following like the dashboard branch of the IV repository as mentioned here, but we have now updated it to like incorporate like dynamical dashboards as well. And yeah, so basically you can provide user input and still be able to sort of get the results that are sort of for the latest run of like the tests filtered. So yeah, maybe I'll show a demo of the like the IV dynamical dashboards portal as well. So just give me a moment. Dynamical dashboards application. So yeah, this allows you to view the latest test results for like any of the tests based on like the filtering sort of parameters that you give. So yeah, so the way it works is that like whenever a test is triggered, it sort of updates its result like pass or fail, like in a MongoDB sort of database, and this sort of application fetches the result from like MongoDB database in real time. So yeah, so let's see how do we use it. So first we need to enter the module that we would like to see the test results for. Let's say I want to see the test result for stateful module, and then like it updates the sub module based on like the module entered, so I can have it for converters, modules, layers, optimizers, norms, and so on. Let's choose layers for now, and then we need to choose a backend, let's say NumPy, and we'll also be incorporating like the backend versions and the front end versions. So front end and the front end versions, and then we'll also sort of make like these multiple in the future versions, so that you can see the results for uh, multiple submodules and backends like in a single sort of selection. So yeah, let's check for this, and then we'll click the submit button. So yeah, this fetches the results for all the stateful layers NumPy sort of test combination. So the test sequential layer is success, let's say, and we can also like click on this to reach the corresponding actions. Let's also sort of check for others, maybe norms. And then if I click there's a single test that was triggered, so we can also like move here. Also let's see for activations. Yeah, so similarly we can change this, and let's say we want to check for TensorFlow front end, it would update these submodules, and let's say I have t types and I click on submit. So yeah, so yeah, that's all. Thanks.